A wet towel concentrated on one side can turn a washing machine drum into an off-center rotating mess. If rotational speed doubles, the forcing produced by that imbalance rises by roughly 4 times. If the motor simply continues accelerating, the tub can strike the cabinet, the machine can move across the floor, and loads on the bearings can rise sharply. Yet a modern washer can remove a large amount of water by spinning at high speed. It does not truly balance every garment the way a technician balances a wheel with fixed weights. Instead, it suspends the entire tub on springs and dampers, probes the load through the drive system, and decides when to accelerate, when to back away, and when to abandon the maximum spin speed. The most important decisions occur before the familiar high-pitched spin begins. In a front-loading washer, clothing sits inside a perforated metal drum. The drum rotates inside a sealed outer tub that contains water and routes it toward the drain pump. The drum shaft passes through bearings and is driven either directly by the motor or through a belt. The outer tub, however, is not rigidly attached to the cabinet. Springs support it while dampers connect it to the frame. Heavy counterweights attached to the tub do not correct a clothing load that changes during every cycle. They increase the moving mass and modify the dynamic response of the suspended assembly, making the motion produced by a given imbalance easier to control. The springs support the assembly and allow displacement. The dampers dissipate energy so the oscillation does not continue growing from one revolution to the next. The remaining system includes the motor, power electronics, and controller. From speed feedback, electrical current, estimated torque, or dedicated motion sensors depending on the design, the machine can determine whether the drum is rotating smoothly or being pulled by an off-center mass once per revolution. Not every washer uses the same sensor arrangement, but the common objective is to assess imbalance before entering a dangerous speed region. The floor and installation are effectively part of the dynamic system. Adjustable feet must support the cabinet without rocking, and shipping restraints must be removed, so the suspended tub can move as designed. A sophisticated controller cannot fully isolate motion if the cabinet alternately loses contact with the floor, or if the tub is still mechanically locked to the frame. An eccentric mass produces a rotating periodic force. Its magnitude depends on the unbalanced mass, its distance from the axis, and the square of angular speed. A small imbalance that seems harmless at low speed can therefore become severe as speed rises. The suspended tub assembly also has natural frequencies. During acceleration, drum excitation must pass through resonance regions of the mass spring damper system. Tub motion can become large there even before the final extraction speed is reached. Dampers that are too weak allow excessive motion. A suspension that is too stiff transmits more force into the cabinet and floor. Engineers cannot solve the problem simply by locking the tub rigidly in place. The laundry is not a solid counterweight. Garments slide, cling to the wall, retain different amounts of water, and can roll into a single bundle. Every time the drum reverses, mass distribution may change. How can a controller assess a load that is soft, wet, and continuously changing shape without seeing inside the drum? There is another complication. At low speed, garments repeatedly fall through the drum. Above the plastering speed, they remain pressed against the wall. Measurements made below that transition describe tumbling, while measurements made far above it are increasingly affected by motion of a suspended tub. The useful test region must therefore separate the signature of the load from the response of the suspension. The machine begins with slow motions that separate and distribute garments around the circumference. It then accelerates to one or more test speeds. With a well-distributed load, the torque required to maintain speed is comparatively steady. When a heavy region rotates upward and then downward during each revolution, gravity and motion of the suspended assembly create periodic variations in motor speed, torque, or electrical power. The algorithm does not need to identify the position of every garment. It needs to measure the magnitude of the periodic signature and compare it with a limit appropriate to the load and intended speed. Some methods probe at a speed where the laundry remains against the drum wall but the tub has not begun moving excessively on its suspension. Other methods monitor motor power over several speed steps to estimate how much imbalance can be tolerated at a higher operating speed. If the evaluation fails, the washer decelerates. As centrifugal action decreases, garments fall away from the wall and can be tumbled or reversed into a new distribution. The machine then tests again. If imbalance remains excessive, the controller may repeat the process, use additional redistribution motion, or select a lower extraction speed. It does not create perfect balance. It finds a state that remains within the mechanical limits of the appliance. Once acceleration is permitted, the suspension handles the remaining motion. Springs let the tub center move around its equilibrium position, counterweights alter the assembly response, and dampers remove oscillation energy. The cabinet appears stationary not because the tub never moves, but because tub motion is isolated and constrained within the designed clearance. Counterweights also make clear why appliance mass is not simply wasted material. For the same eccentric laundry mass, a heavier suspended assembly experiences less acceleration. That benefit must be balanced against shipping mass, structural loads, cost, and the energy required to change speed. The final design is a compromise rather than the elimination of motion. A complete extraction cycle begins as the pump lowers the water level. The drum turns slowly to distribute the load. The controller raises speed into a measurement region and reads the response of the motor and suspended assembly. If the imbalance signature is too large, acceleration stops. The washer releases the garments from the wall and tumbles them into another arrangement. When the load reaches an acceptable condition, the motor accelerates through successive speed stages. Clothing presses against the perforated drum. Water passes through the holes, and the pump removes it. While crossing a resonance region, the acceleration strategy and dampers must work together so the machine does not remain at a large response for too long. At high extraction speed, monitoring continues because the bundle can change as water leaves it. If conditions deteriorate, the maximum speed is reduced. The result may be laundry that retains slightly more water, but the bearings, suspension, cabinet, and floor avoid much greater dynamic loads. This is a deliberate trade. Some extraction performance is exchanged for durability, noise control, and mechanical safety. This also explains why the displayed remaining time can increase. Redistribution attempts and staged acceleration consume time that a simple timer cannot predict in advance. The cycle duration changes because the machine is responding to the actual mechanical state of the load, not because the clock has lost track of the program. A washing machine does not defeat imbalance with one magical component. It uses 3 coordinated layers: redistribution through controlled drum motion, state detection through the motor response or sensors, and vibration isolation through mass, springs, and dampers. The controller allows speed to rise only when the system can tolerate a force that grows with the square of rotational speed. When a washer slows down in the middle of an extraction sequence, it is not hesitating. It is measuring a rotating machine whose mass distribution keeps changing before allowing it to reach its highest speed.